Hey everybody, it's time for our electrochemical cell lesson. Gather round. Excellent. Here we go. Today is June 8th, and we're going to talk about making redox reactions useful. Many of your favorite gadgets, such as your phones, are run by the use of batteries, and batteries use chemical reactions, redox reactions specifically, to generate electricity. How cool is that? I've been doing a little bit of drawing this morning. I hope you like my ox and my little cat here. I've got a red cat and an ox. Red cat and ox. We'll talk more about them a little later. So our focus today is one type of electrochemical cell, and it's called Voltaic or galvanic cell. Let's start with a warm-up. We're going to start by analyzing this chemical reaction. We're going to determine whether or not it is a redox reaction, and the first step we have to do is assign oxidation numbers. Of course, it's very useful for you to have your periodic table out and table E for this part. Also, going to pages 140 and 141 in your UpGo book will be useful to remind you of the rules for assigning oxidation numbers. I'm going to go through those rules right now. Any free element, such as solid zinc, will always have an oxidation number of 0. We then have a compound, copper 2 sulfate. We have copper with a +2 charge because the sulfate ion has a -2 charge, and that balances out to a 0 charge. We need to look at oxygen separately because sulfur has multiple oxidation states. We will note that oxygen has a -8. The copper is a +2. So by default, the sulfur must be correct, +6, to get a +8 and a -8 net 0 charge. Okay. Then we create zinc sulfate. Well, we know our oxygen is -2, so I'll just write that there. That's a -8. We're going to look at zinc. The only option for it is a +2. And then by default, sulfur must be +6 again to give a net 0 charge. And finally, we end up with copper as a solid. It's free, it's a free element, and therefore it's got a net 0 charge. Our next step is to identify whether this is a redox reaction. Zinc goes from a 0 to a +2. Woohoo, we have a redox reaction. And because zinc is becoming more positive, that means it's got a loss of 2 electrons to become more positive, and that is Leo. Zinc is said to be oxidized. Copper, here it is. Copper changes from a +2 to a 0. It must be gaining 2 electrons, and that is Gur. That is the gain of those electrons. So now we know we have an oxidation reduction reaction. We're going to write the half reactions. We always start nice and simple, just saying, well, here's our zinc with no charge. It becomes zinc +2. It had to lose 2 electrons, so we're going to write those 2 electrons on the right-hand side. We're going to go now to the copper. That copper started as a +2. It had to gain 2 electrons, so I'm going to write that, and it became that copper with a 0 oxidation state. They are balanced in charge. So I don't need to do any multiplication here. I will put them together, zinc plus copper, and there's our overall redox equation. Zinc here is oxidized, and this copper is reduced. Okay, so we're going to move on here. The voltaic or galvanic cell is one type of electrochemical cell that you will be learning about in this unit. The next type of electrochemical cell is called an electrolytic cell. You will learn about that in our next lesson. So, voltaic or galvanic cells are really, really amazing. Why? Because they have chemical reactions, specifically redox reactions, that can produce electricity. And if you recall from previous units, anytime you have electrons flowing or ions flowing, electricity can be generated. How do we generate electricity? There are a few parameters that must be met. Number one, we need to physically separate the two half reactions. And in my upcoming example, here are the two half reactions that occur in the galvanic cell I'm about to show you. In doing so, I create two half cells. So there's separate areas where the half reactions are occurring. Now those half cells are connected to each other by, number one, a salt bridge. And a salt bridge is composed of salts in an aqueous solution. And when salts dissolve in an aqueous solution, they create free-flowing ions. And the purpose of the salt bridge is to balance the charge built up from the redox reaction. Hopefully this will make more sense in a few minutes. The second way half cells are connected is by an external circuit with a basic voltmeter or some kind of device. Here, the device is our clock. The device could be your watch because this watch is running on a battery. So I have here a very simple drawing of an electrochemical cell. The table we want to go back to, table J, is good to predict a redox reaction, whether it will occur and how the two metals will interact. So let's look at my electrochemical cell here, and I'm going to label it in depth in a minute, but I want to highlight that this bar here represents zinc metal. This bar here represents copper metal. And when I look at the activity series, I'm looking for zinc or copper. Oh, here's zinc. And here's copper. What this is telling me is that zinc is more active than copper. If you recall, metals are losers. Metals will lose electrons. That means that zinc will be more readily able to lose its electrons. And when we have that happen, zinc is going to give or lose electrons and give them to copper. Zinc will be oxidized, copper will be reduced. So zinc can be called a reducing agent because it's basically forcing copper to receive those electrons. Why? Because this is higher up on table J. It's a more active metal. Okay, so labeling this electrochemical cell, this specifically would represent a voltaic cell. As mentioned, that zinc is a metal bar here, and it's an electrode. Copper is also a metal bar electrode. And I'm going to go back to my lovely drawings that I showed you before. Anox and red cat. This is going to help us. The anode, new word for you. The anode is the site of oxidation. The cathode is the site of reduction. So when we have a galvanic cell, as shown here, one of these electrodes is the anode, one is the cathode. We know that zinc is the anode, and it's the negative end of this electrochemical cell. How do we know that? This is the anode where oxidation occurs. It will lose its electrons. The electrons are going to travel as they are lost along a wire, and they're going to continue traveling down to the cathode where reduction is occurring, is the positive end of this galvanic cell. So just going back to our warm-up briefly here, we wrote half reactions that do apply to this electrochemical cell. We have solid zinc. When zinc oxidizes, it loses 2 electrons to become zinc plus 2 ions. Those 2 electrons are what's traveling along this wire and coming down to copper. Each copper ion is receiving those 2 electrons, and it's becoming solid copper. Now, this already is solid here, but I got to talk to you about what's inside these beakers, okay? So this electrochemical cell has 2 beakers, and that equals the half cell. And suspended in those beakers are these metal electrodes. Inside the beakers here are aqueous solutions of, in this one, there's zinc sulfate, and in this one, there's copper 2 sulfate. And one thing I want you to think about, zinc sulfate, when it's dissolved in water, becomes ions, and that copper, when it's dissolved in water, barely fitting that in there, becomes these ions. Okay, so we have free-flowing ions floating around these 2 metals. These 2 metals are connected to each other by a wire that meets up with a voltmeter or some device. Electricity is created by free-flowing electrons and or free-flowing ions. So we've got both things going here. So let's add to our labeling here. Okay, I want to talk about this ever important salt bridge, which, as I mentioned before, is a way to connect our 2 half cells. This salt bridge is going to contain a salt, and salts are ionic compounds. I'm going to give you one example of a salt, potassium nitrate. But potassium nitrate dissolved in water, and just like these salts here, it dissociates into potassium ions and nitrate ions, K plus, NO negative over 3. And this salt bridge is going to serve to balance out the charge. So what ends up happening is the NO negative over 3 ions go in this direction, and the K positive ions end up going in this direction. There's like a little porous plug at the end of the salt bridge, but it allows those ions to kind of go into solution here, because as this solid zinc loses its electrons, the zinc ions go into solution here, and that keeps happening as oxidation occurs. As the copper receives these electrons, the electrons travel down here. The Cu plus 2 ions grab those electrons. So the copper 2 sulfate ions generated in the solution go and grab those electrons that are traveling down through this copper metal. What happens here is the mass increases because these copper +2 ions are grabbing the electrons traveling down here and depositing solid copper here. On the other hand, this zinc, we have that zinc, the solid zinc, mass decreases. It's releasing electrons here, and then the zinc ions go into solution. So just to go back to the salt bridge here, we have, extra positive ions going into solution here. So the negative nitrate ions are going to go and kind of balance out. We don't want an over accumulation of a positive charge in the solution here. Likewise, we have an uptake of positive ions here, leaving these sulfate ions in surplus, that negative sulfate. And the potassium is attracted to that. That salt bridge is balancing out those charges. Now, what I've done here is I'm taking these metal electrodes and looking at a microscopic view of them. I have a zinc anode, okay? This is a piece of metal, and these circles represent the atoms of zinc. That zinc, as it oxidizes, it releases zinc ions into solution, and 2 electrons for every zinc atom get released, and they're going to travel over to the cathode side. Now, the cathode is made up of solid copper. It's receiving those electrons. Copper +2 ions are actually the part that's getting reduced. These are in solution, and they get attracted, right? They gain those electrons, and they're actually depositing these extra copper atoms onto the surface of that electrode. So this electrode gains mass, this electrode loses mass. And here were those half reactions. You will be watching a short video that'll show this more animated. I would like to conclude this lesson with an explanation of our potato clock. The potato clock is a galvanic cell, and our potatoes here are actually the salt bridge. Our clock is equivalent to the voltmeter portion, and the black wire is shown right here. The black wire is the anode, and this anode is actually made up of zinc metal. The red wire is the cathode, and that's actually copper metal. So the black is the anode, the red is the copper cathode, right? These wires are attaching to the back of our device, our voltmeter, in this case a clock. So the electrons are traveling along to the back of this little clock, all right? And then they are traveling along to our cathode end, the copper end. The salt bridge, the potato, actually has phosphoric acid in it. The phosphoric acid serves to create that salt bridge that is balancing out the charge changes created by the flow of electrons towards that cathode. If I were to take these out, we would stop time, folks. Pull those out. I no longer have the salt bridge in there. No more electricity is generated. Put them back in. We're back on time. I hope you enjoyed this lesson. Have a great day. Bye.